We've seen that some atoms are capable of accommodating less than 8 electrons, such as boron and beryllium. In this program, we're going to take a look at some atoms in the third period and beyond that are able to exceed 8 electrons, or the octet rule. They can do that because they have vacant d orbitals. I'll begin by considering phosphorus pentachloride and its Lewis dot diagram. We'll start by determining the total number of electrons that we have. In this case, 40 electrons, or 20 pairs. We begin by putting phosphorus in the middle and then surrounding it by the 5 chlorines. The first place we place electrons is between the atoms. That then takes care of 5 of my pair. Now I'll complete the octets of the atoms on the periphery. And at this point, I've used all 20 pairs of electrons. If we examine the central atom, we can see that it has accommodated 10 electrons, more than the octet rule. Those 5 regions of electrons would spread themselves out in the following shape. This is called trigonal bipyramidal, where we have 5 electron regions, and all of them are bonded. Now let's consider sulfur hexafluoride. Again, determine the total number of electrons. In this case, 48 electrons, or 24 pair. Start with sulfur in the middle and surround it by the fluorines. Then bond the fluorines to the sulfur and complete their octets. At this point, I've used up all 24 pair. My central sulfur in this case has 12 electrons, or 6 pairs. Those 6 regions would spread themselves out in the following shape. This is called an octahedral. Shapes of molecules with expanded octets introduce new geometries based on the octahedral or the trigonal bipyramidal arrangement. These are summarized in the table below, based on the number of regions and the number of unbonded or lone pairs. Let's look at how this works by considering xenon tetrafluoride. First, we determine the total number of electrons, 18 pairs in this case, xenon in the middle, and 4 fluorines. We bond the fluorines to the xenon and complete their octets. At this point, I've used up 32 electrons, and I need to replace the remaining 4, and I'll give them to the central atom. We can see here that the xenon now has 6 electron regions, so I'm based on this row. An examination of the Lewis dot diagram shows that there's 2 unbonded pairs, which leads me to a square geometry. And here's what that would look like, with the square forming coming in and out of the plane of the slide, and the 2 unbonded pairs lying above and below. Let's try a question based on these geometries. Compare the geometries of this anion and this cation. I'll start off with the cation, with the positive charge. We'll determine the number of electrons available, and in this case, 34, or 17 pair. Iodine goes in the middle, surrounded by 4 chlorines. Bond the chlorines to the iodine, complete their octets, and at this point I've used 32 electrons. The remaining 2 I give to the central atom, which now, as we can see, has 5 electron pairs around it. Those 5 electron pairs would begin with the trigonal bipyramidal arrangement with 1 unbonded pair. That's called the seesaw geometry. You'll note that I placed the Lewis dot diagram in square brackets, which is conventional when we're dealing with ions. Now let's consider the anion. Total up our electrons, and this has an extra pair due to the negative charge that resides. We begin with iodine in the middle, surrounded by 4 chlorines, bond the chlorines, complete their octets. 32 electrons are used at this point, and the remaining 4 are placed around the central iodine. Again, we'll put it in square brackets because it's an anion, and we'll identify the number of regions. So this will be based on the octahedral with 2 unbonded pairs, and we've seen this before. This is a square geometry. If you have any questions, don't hesitate to ask, and thanks for watching.